Welcome everyone to the latest HACC Tech Talk, and this is the first in our summer 2024 series. My name is Colin McCabe from the AMD University program, and I'm very pleased to be able to welcome our two speakers for today. Before I do that, I'd like to briefly introduce our HACC program and this series of talks for anyone new to the program or these sessions. So the HACC Tech Talks are intended to highlight some of the applications and research related to the Heterogeneous Accelerated Compute Clusters program. So this program is a special initiative from AMD to support novel research in heterogeneous accelerated computing. HACC centers have been set up at partner universities around the world, you can see on the screen, and our newest HACC is IISc, the Indian Institute of Science in Bangalore. Each HACC consists of compute nodes enabled with AMD EPYC, Alveo, Instinct, and Versal computing hardware. Participants in the HACC program can access these nodes remotely for their own research. So if you are a researcher working in high-end compute and related fields, we invite you to join the program. And you can find details on the webpage shown on the screen, amd-hacks.io. So over to our speakers. So our first speaker today is my colleague, Dr. Mario Ruiz from the AMD University program, and he'll present on XDNA, also known as our AI engines and their programming model. So Mario, I'll invite you to go ahead and take the share, and I'll just say, please post any questions in the Q&A. We'll try to address those at the end of each presentation. And if you would like to discuss something in more detail, I'll refer you to our HACC program user community, which is intended for exactly these sort of discussions. You can get in contact with the speakers and other researchers working on heterogeneous computing. So over to you, Mario.
Can you see the screen,
Yeah.
Kaha? Well, thank you, Kaha, for the introduction. And today, in this first Tech Talk for 2024, I would like to start by introducing the XDNA architecture and its programming model. And we're going to see this is a slightly different architecture that is designed to try to get more power efficient for certain kind of workloads. And before we start, just want to mention that AMD is uniquely positioned to cover all of the compute demands in the current scenario. So we have product lines ranging from CPUs all the way to SmartNICs and DPUs. And in particular, today I'm going to be talking about the XDNA architecture, which is present in a few product lines, which this technology is enabling us to deliver efficient AI inference all the way from the data center to the client. And towards the end of the presentation, I'm going to mention some of the products or the development board where this technology is available, so you can get started and start using this amazing technology. So, but what is the AI engine technology? And the AI engine of the XDNA is what's also the AI engine technology, and it was initially released in 2019 as part of the Versal Adaptive SoC. And this is a piece of silicon on your chip that is an array or two-dimensional array of very long instruction word, single instruction, multiple data processors. And they can run over 1 gigahertz. And they have been designed and engineered to provide power efficiency for ML and DSP workloads. The idea of this architecture is scalable. So depending on the device and your needs, you can go all the way from 8 tiles up to 400 tiles in the bigger devices. There is terabit of bandwidth within the array, as well as moving data in and out of the array with the rest of the system. And more importantly, these are software programmable. Compared to the traditional FPGA fabric, you can write your programs in C, C++. And in the second part of this presentation, I'm just going to show you how you will go about to program this technology. So maybe to motivate this architecture, what is different from a traditional multi-core architecture? If you look at the left-hand side, you have the traditional cache-based architecture where you have your cores, your level 0 cache, and the cache hierarchy go all the way to the external memory. So in this scenario, your program just want to read some data from memory, but is it uncertain where this memory is going to live? Is it in level 0 cache or level 1 and so on? So the execution of your program tends not to be deterministic because the time that it will take to fetch this data is unknown a priori. Also, this amount of cache, of this cache hierarchy, consumes a lot of area in our silicon device, hence requiring a lot of more power to actually be able to feed that data to have this nice programming model, if you will. Additionally, some of the data ends up being replicated because of the different level of caches and the different where the caches are allocated with the different cores. In contrast, in the engine array, we have a dedicated local memory for each compute core. And this is a relatively small memory, but the idea of this data flow architecture, spatial data flow architecture, is that the execution of the data will drive the execution. So you when you program this architecture, you need to specify a priori how the data is moved, and the compute is only going to happen when the data is available at the input of the kernels. So on top of that, this architecture includes this array of this mesh interconnect here to do efficiently data movement within the array, and we're going to see this in more details in a few seconds. So just to highlight, there is no cache in here, and hence we can guarantee determinism in this application. And for these kind of applications that will map well for the engine array, you will end up requiring less memory, so hence saving some power as well. So with this mesh or this two-dimensional array, you can have you've got a few different ways of communicating the different compute elements. And if you just want to communicate via memory, we're gonna see this in more detail how this happens. So you have the data flow pipeline where the communication happens through the memory. You can also have more complex data flow graph where a single AI engine can forward the data to multiple compute tiles. In contrast, if you try to move data to non-neighbors, you can use the streams or this array, this mesh of interconnects that was shown in the previous slide to move data efficiently between non-neighboring tiles. Also do multicasting. The multicasting here is for free, replicating a piece of data to multiple cores is for free. And also we have additional features like cascading a stream that allows us to forward partial results from one compute core to another. So with that, I just would like to introduce a little bit more of the hardware specs of this architecture. So some of the terminology, as I mentioned, this technology, the engines array, were introduced in 2019 with the Versal Adaptive SoC. And then we have the engine array, which is this two-dimension array, of course, where you can see then that this is composed of engine tiles, and the tile is the core itself, the local memory, all of the interconnect memory interfaces, the stream interconnect, the stream interfaces, and the cascade stream. And finally, the AI engine is the ISA of this architecture, and we'll just talk a little bit more about this in a few slides. So this is a tile-based architecture, as I mentioned, where we have the vector processor here in green, the local memory, DMAs to move data efficiently with non-neighbors, and then the array of interconnects that we have. The red arrows here are communication with the local memory of neighbors, the north, south, east, and west. And then we have the interconnect in black, which is allows us to move data to non-neighbors, and also allows us to move streams, Axie4 streams to the vector processor. And as I mentioned, the cascade stream. So the local memory is a small memory, but it's very efficient. You can achieve over 200 gigabytes per second in here, and of bandwidth, and access the memory on the north, south, east, as west, as I mentioned. And again, I'm gonna be showing some slides how this happened. On top of that, we have the DMA, which gives us the capability of the data movers to move data from local memory to another core that is non-neighboring to us, or to the interface tiles that's going to move the data to the rest of the system in the case of the Versa. The interconnect is often, as I'm showing here, often in conjunction with the DMA to move data to other cores, but it also allows us to do data movement using streams. So we'll see that there are two ways of moving data here, streams and buffers, and the interconnect will allow us to do both of them. Again, this is a very efficient design, and although there is only one arrow shown in here, each of these, there are multiple channels in all of the directions. And finally, we have the cascade interface, and this is more of a DSP type of processors where the result of the accumulators from one vector processor can be moved to the next vector processor very efficiently without having to use the rest of the infrastructure. So now if we look at the vector processor, the processor, the ISA, this is a very a highly specialized processor. So this is what, there are multiple modules in here, multiple units that can run in parallel concurrently in the same clock cycle. We have the scalar unit, a vector unit, we have 2 loads units and 1 store unit. This is just to communicate with memory. We have the fetch and the code unit, interfaces to memory, and streams, as I mentioned before. The scalar unit is a simple RISC processor that allows us to do some scalar computation. It's a scalar LAU, and support for nonlinear functions is there. And this is programmed just using a standard C language. The vector processor is the interesting part in this technology, and it's where we can actually get the performance out of this technology. And it's divided in 2 parts. We have the fixed point vector unit and the floating point vector units. And these 2 units are completely independent, but although they can't run at the same time in the same clock cycle, but they can be used. And those units allows us to do support multiple different precisions, as I'm going to show in one slide. And to program this, we need a spatial vector data types that are encapsulating on what we call the AI Engine APIs. Again, a little bit more on this in a few slides. This architecture, in this architecture, we can get different level of parallelism to achieve higher performance in your application. And the first one, as I was being hinting, is the instruction level parallelism. The AI engine has 7 different units or 7 different units that can be executed in the same cycle using these VLIW instructions that has 7 ways. So there are operations for loads, 2 loads in the same clock cycle, 1 store. Maybe you can grab the laser pointer. So 2 loads operations, 1 store, 1 vector multiplication. This is using the fixed point or the floating point. Then we have 2 move operations. This is to move between registers, and the scalar operations. So as you can see, up to 7 operations in the same clock cycle. Then the other level of parallelism is data level parallelism. Each of the floating point and fixed point vector processor operates on vectors. Depending on the data types, there are different number of lanes, but you can imagine here just a traditional CMD kind of processor with the same operation is applied to all of the lanes of the 2 input vectors. And the final one, the final level of parallelism is the multi-core. Depending on the device or that you are using, you can go from 8 AI engine tiles up to 400 AI engine tiles. So if your application is highly scalable, you could map it to up to 400 AI engines and multiply the speed up significantly. Just want to mention that each of these AI engines run completely independent of each other. The only dependency here is when the data is available at the input of the AI engine. Okay, with this architecture, we can support different data types, and depending on the data type is the number of multiplication accumulations per clock cycle that we can achieve, and this is listed in this table. And just I have highlighted a few of them in red in here. If you are using int8 for both operands, you can get up to 128 operations per clock cycle multiply accumulates. For int16, 32, and then for single precision floating point and for int32, you get up to 8 multiply accumulates per clock cycle. I also mentioned that we can communicate or move data, the kernels of the vector can operate either on buffers, using buffers, or Windows sometimes referred to Windows as well, or streams. And in this table, I'm listing the performance of each of them. If you're using buffers, the vector processor can read 256 bits per clock cycle and do 1 store, 256 per clock cycle. Whereas if you are using streams, you can do either 2 reads and 1 write, or one read and 2 writes of 32 bits each. So there is a little bit of a difference in that in performance. So it's always best just to try to use buffer as much as possible. Now, if we look at the memory, which is also a very important piece of this technology, so the AI engine model is just next to the vector processor, and it's 32 kilobytes in the first generation of this architecture, divided in 8 banks. And there are arbiters and synchronizers here to make sure there is no data corruption. And typically the banks are paired in bundles to be able to achieve those 256 bits and write operations. There is a continuous addressing in the memory space with these banks. And again, this is local memory. For each AI engine array, we have one of these 32 kilobytes local memory. And if you can see here, these red arrows coming in and out of the memory models are the communications with the neighboring AI engine tiles. And it's the one representing the two loads that we can do from neighboring memories or from local memory as well. The other component, very important, is the data movers in here and we tend to use the data movers when there is a need to transfer data between non-neighboring AI engine arrays, AI engine tiles. So on this, there are two directions, incoming and outgoing streams. And for each of those, we have two different DMAs that can access the local memory space. And as I said, this is just for transferring non-neighboring, to transfer data to non-neighboring arrays or the memory tiles, sorry. One thing that we like to highlight in the first generation, the kind of memories or the neighbors that you can be accessed from a particular AI engine. In the case of even roads, you can access the memory in the north, south, west, and your own local memory. And this memory can be used either to extend your local memory, to multiply by 4, or to share memory with your neighboring AI engine array, and engine tile, sorry. And for the odd rows, you can access the memory in the north, south, your own local memory, and the one in the east. So again, for the first generation, the diagonals don't have the same access pattern depending on the rows. So it's something to consider if you want to replicate a design from just have a design that you want to stamp out across the array. You need to consider this kind of specifications of the architecture. Okay, so that's covered a little bit of part of the hardware architecture. There are a lot of more details that could be covered, but in the interest of time, I'm just gonna move to the programming model, which is as important as well. So as been saying, this is a spatial data flow architecture. And what this means is that the flow of the data is what drives the computation. And to describe the computation for this architecture, we need to use data flow graphs, where the nodes here in blue represent the computation and what's going to be mapped to the vector processor or the scalar processor, and the edges represent the flow of data from source to sinks. And again, so the edges are the connections. This can be from the inputs of our the inputs to our array, the outputs as well, or the source and sinks of our compute nodes. And we can use this kind of data flow representation to describe any applications that are going to map into the AI engine array. As I mentioned, the flow of data is what drives the execution or drives the computation, and a kernel won't run or won't execute until the data in its input is valid. Again, to mention, so the edges of these data flow graphs are going to be mapped to any of these interfaces in our array, either the memory, the stream, the DMAs, or the cascade interfaces. And the nodes, which is the computations, are going to be mapped to the vector processor. Okay. So because this is a CMD architecture with VLIW instructions, there are some APIs that you can use to program your computation to maximize the benefits of these architectures. Just in the interest of time, I'm listing them in here. You can look at the AI Engine API user guide in the UG 1529, where you can see all of the different components or different kind of calls that you can do for this architecture. I'm going to be showing some of them in a few slides just to show you how you program this array. Okay, now a little bit on the programming model, we can see a very simple example for a single kernel. This is just where you have one input, one output of your array, and you have one compute kernel. Again, the kernel is going to be written in C, C++, and using the AI Engine APIs to target the vector processor. Once this is compiled by the AI Engine compiler, the executable will be loaded into the vector processor and executed once the data is available in the local memory. So this is a simple example of kernel program. It's a FIR filter with asymmetric coefficients, and just gonna go step by step to describe the different pieces of this kernel. First, we need to include the adaptive data flow library where the definitions of the data types are there, as well as the calls of the APIs calls that we can use to program this architecture. Then we have the function definition, the definition of this kernel, and kernels for this architecture need to return void. So, and then we have the spatial data types in here, which are windows, and you can consider windows as buffers in memory. And these are spatial data types that allows us to do multiple read from this pointer, multiple elements in the same clock cycle. And we have one input and one output. Then we have the way to define vectors. We have these APIs, the AI vector, where we specify the data type as well as the number of lanes in this vector. We can also initialize this from constant or coefficients with this load elements from this particular variable here. And then we can also start accumulators. Accumulators is where the result of our multiply accumulations or our multiplication operations are going to be stored that then need to be downshifted to be written to memory. Just to read and write from these pointers in here, from this reference to the buffers, we have a special APIs, Windows read increment. And what this API does is reads 8 elements of this particular underlying data type, in 16 in this case, and moves the pointer 8 positions as well. So we have the 2 in here. And then similarly for the Windows write increment, so you are written the number of elements in this vector, and then moving the pointer, again, the number of underlying vectors. We have also these optimized APIs in here just to operate with FIR filters, but similarly, there are APIs for matrix multiplication that simplify the process. And these APIs will also have their own operators just to do multiplications and also multiply accumulator. And there are also spatial APIs to manipulate vectors like insert, extract, or replace inside of a vector, so you can move or shift things around within the vector itself. That's one part, which is essentially describing the computation of our kernels. But then we also need to describe the connectivity. And the connectivity is the part where we specify how the data flows in our array. And this is very similar. Again, we need to include the data flow library. And every single connectivity or adaptive data flow graph needs to be derived from the public class graph. And then we specify our kernel. This is essentially the computation. We define the kernel, and then we create a kernel where this gets associated to the particular function prototype. We also create the input and outputs from our graph, and this is going to be the interfaces with the rest of the design outside of the engine array. We can give it a name. We specify how the number of bits that are used on the access stream. Additionally, we can provide a file for simulation and the frequency on the program logic. And this is the other important part, is where we specify the connectivity between the different parts of our graphs. And this is doing the connections of our input with the input of our kernel, and then the output of our kernel with the output of the graph. Notice this argument in here in the connect, and this is the number of bytes that are needed for this execution, or for each execution of the kernel, there are needed 128 bytes in this buffer. So until there are no 128 bytes, the kernel is going to be in an idle state waiting for that data to be ready. And then finally, we need to specify where the kernel lives and the budget that this kernel is allowed to run in our AI engine. There is also a piece which I call it the test bench, but this defines which graph, because we can have multiple graphs, which graph we want to compile, and then we have guards operators here. So this only gets executed in simulation, and we can simulate this with cycle accurate simulation in your x86 machine to run the simulation with this particular APIs in here. That was a very simple example. This one is slightly more complicated, more involved, where we have two kernels, K1 and K2, weighted sum and average diff, which are highlighted in red. And then we have three connections from the input to the output, which I highlighted in blue. And what you can see here, this is the output of the ByteDist tool, which are the tools that we use to compile this. Once that gets compiled, you can visualize this visual representation where you can do cross-probing where these kernels live, where the source code is, and where the connections are. So a little bit more involved. I've been hinting that there are, this is what I mentioned is the first generation, but the XDNA is a multi-generation architecture. And currently we are in the second generation, which is the AI ML, which has been further optimized for ML workloads. The idea or the concept of the architecture is very similar, but they're having optimizations in particular in the data types. So there are data types that are more common in ML type of workloads like VLIW 16 and int4. We also have increased the number of the amount of memory in the local memory, doubling to 64 kilobytes. We also have added a memory, what we call memory tile. This is a tile with 512 kilobytes of memory at the bottom of each column. And this is typically used to do Marshall of data. You can split data in here and replicate it to multiple tiles. And finally, we have the data movers have been further optimized to be able to operate with tensors, what we call the multiple dimensions data mover support are in there. And another thing that has been increased or changed is that the pattern for memory neighbor communication with neighbor is exactly the same in all of the rows. Essentially, you can access again the north, south, your own local memory, and the memory in the west. I'm reaching the end of the presentation. Just to want to mention some of the development boards or technologies that have the engine array of the XDNA technology. You have the VCK190 featuring a VCU 1902 device. The VCK 5000 is more a PCI enabled board, again with the same device, VC 1902. And then the VK280 is a relatively new development board with the AI engine ML array in there. So I'm gonna leave this for you just to have a look at that. I just scratched the surface of this technology. If you're interested in more, you can go and look at this, the versatile adaptive SoC design process documentation, where you will have links to the documentation for the different components or the different parts of this technology, programming model, adaptive data flow, and the different pieces of the versatile design. We also have this AI learning path. We're gonna leave in here some references, some of the material, the technical material to learn a little bit more about the different pieces. In the AMD University program, we also have a tutorial that you can access just to program the AI engine with some example designs, also project-based examples where you can learn a little bit more about the architecture and get hands-on experience with this. There are also these tutorials for the AI engine for both AI ML and AI for different kind of applications where you can learn and see example designs. And maybe just to conclude, as I say, this technology is not only available in the versatile, those big development boards, but also in last year, it was announced that this technology was available in what we call Ryzen AI, which is this the APUs that go in your laptops. So now this technology is also available at the fingertips of your laptop. So we have this Rialto tutorial framework where we expose and make this technology available for everyone to use in their own laptop or mini PC. And just leave this for your reference. Thank you for listening. And I think I went a little bit over time.
Yeah, thanks a lot, Mario. So we'll try and squeeze in a couple of quick questions and we'll get to some of the other ones in the chat. So there's a question partially answered in the chat, but the second part of that question was, what bottlenecks are we facing in the AI engines? Maybe you could quickly highlight some of the areas that you need to consider when designing with AI.
Yeah, so one of the things is the bandwidth or the number of input outputs from the array itself to the rest of the device. That's one of the bottlenecks that's limited to, let's say, I think there's, depending on the device, that's changed, but depending on the device, you can have, let's say, a limited number of channels there. So the I/O, some applications tend to be I/O bound, and then sometimes also the bottlenecks will be just try to optimize your application to fully utilize the CMD. And in some cases, if that's not the case, your application, instead of accelerating, you can end up decelerating applications.
Yeah. Okay. We'll try and squeeze one more in. So Mario, how is the addressing of memory handled to enable access by adjacent AIEs? So how do multiple AIEs access the same memory?
Yes, there are locks or synchronization mechanisms. Essentially, when a piece of the memory, a buffer is being used for a particular AI engine, that region of memory is locked and can only be accessed for that particular core. When that memory is released, another core can access that, and that's done in combination with the arbiters that there are at the top of each memory bank, as well as locks that are part of each component of each engine tile. I didn't have time to go into the details of that, but yeah.
Yeah, and look, Mario, there's a couple of questions in the chat that maybe you can type the answers to. If any questions occur to anyone on the call before the end, if we've some additional time, we can get Mario back to maybe follow up on some of the questions.